Good morning, everyone. It's an honor to us to have Professor Yu in our first conference. Professor Yu is the Roxanne E. and Michael J. Zack Professor in Energy System Engineering in the Smith School of Chemical and Biomolecular Engineering at Cornell University. He also serves as chair of Cornell System Engineer PhD Studies and Associate Director of Cornell Energy System Institute. He is an engineer graduated from Tsinghua University and has a PhD from Carnegie Mellon in 2009. Professor Yu has published more than 120 peer-reviewed articles in leading journals and has an H-index of 50. Some of his research results have been editorially highlighted in Science and Nature. His recent awards, only in the last year, include Computing and System Technology Outstanding Young Researcher Award from AICHE, Cornell Engineering Research Excellence Award, and ACS Sustainable Chemistry and Engineering Lectureship Award. Welcome, Professor Yu.
Thank you very much. Thank you very much for a very kind introduction, and thank you, Professor Saki, for a very kind invitation to have the opportunity to visit here, the beautiful city of Rio, and meeting with many wonderful colleagues in process systems engineering area here in Brazil. So, as introduced by the conference co-chair, I came from Cornell University, and over the past day, quite a few colleagues asked me where's Cornell and how it looks like. So I did prepare a couple of slides to just give you a very brief introduction. So Cornell is one of the 8 Ivy League institutions, together with our, Columbia University, where our opening plenary speaker came from. So Cornell tends to have one of the largest engineering schools in Ivy League, just compare with the size, compare with Harvard, Yale, Princeton, and so on. And we do have a very strong faculty with a lot of Nobel laureate and Turing Award winners. So our campus locates in Ithaca, New York. So this is really in the central part of the state of New York. And the overall campus you can see is right by the lake. It's very beautiful and somehow similar to Rio in a certain way, because you guys are close to the sea and we are just by the lake. So we also have a few satellite campus, the medical campus in Uptown Manhattan, the new tech campus, which is kind of on Roseville Island, and this tech campus really focuses on artificial intelligence, big data, and machine learning. And also have a branch medical campus in Qatar, in Doha. So the main campus is pretty beautiful, I would say, especially at this season of the year, summer, spring, and fall. It's very colorful. You can see many kind of interesting buildings and all kind of styles all around. And in particular, this is really a good place to visit if you're interested in spending a few months, a few weeks, or even a couple of years in the US to study. We typically welcome a lot of visitors from all over the world to come to Cornell. So I moved to Cornell about 3 years ago from Northwestern University, and now at Cornell I was very fortunate to work with a group of very talented students. You can see most of them are now in the photo here, and we took a photo right in front of a classic clock tower at Cornell. I do have 3 students and postdocs still at Northwestern University, and I do want to mention that Dyson Caballero, he's from Brazil. So we do have some connection with Brazil in a certain way. We are funded by a number of projects. So in my research group, specifically what we are doing really focus on 4 major keywords, okay? These would be sustainability, energy, manufacturing, and data. So what we really talk about, in this conference, a lot of topics on Industry 4.0, a lot of topics on smart manufacturing are pretty much the intersections or connections between data and manufacturing. And this is going to be the focus of today's presentation. So when we talk about data, our opening plenary yesterday gave a very nice introduction and really set a beautiful stage. We also see a lot of interesting presentations and poster presentations yesterday talking about many perspectives in terms of data science for chemical engineering. This could deal with issues on data-driven control and operations, for diagnosis, preventive maintenance, soft sensor design experiments, among others. And this particular presentation will focus on an area that has not been touched that much, I would say, by this conference or maybe broadly by the community. And this is an area we call data-driven decision-making. So what does data-driven decision-making means? It's essentially try to reinvent or re-memorize this area of optimization under uncertainty. So when we talk about decision-making under uncertainty, we typically have to deal with a lot of uncertain parameters. These could be kinetic parameters, could be supply, could be demand, could be a lot of external factors. And these parameters usually involve certain uncertainty that we cannot control or we cannot really capture through our decisions. So one way to handle this approach, and it's a classical approach in a certain way, is using optimization methods. And what people typically do is to try to build an optimization model, essentially try to fit this data into a certain uncertainty model. And with this uncertainty model, we use mathematical programming. So this is based on a mathematical model, optimization model, and some optimization algorithm to eventually derive the optimal decisions, okay? So if you're looking at this classical approach, we do have a very nice validation process of closing the loop between the decisions and the models and algorithms. So what that means is if you trust optimization theory and algorithm, then anything you get from this model and the decision will be certainly validated or be proved to be optimal. The missing link, however, is in the upstream here. So in the upstream here, the model we have will be essentially as good as the uncertainty model we get in the end. So if we don't have a very accurate uncertainty model, as you can see from the fitting here, we do introduce a lot of fitting errors. And this could lead to quite a bit of challenge in terms of the final solution and the corresponding optimal decisions. And what we see nowadays in the age of Industry 4.0, in the advanced manufacturing sector, is we tend to collect a lot of data. This could be the sensor data, real-time sensor data. This could be forecasting data. This could be historical data. And many of these data could have very high dimensions. They could be correlated. They could be asymmetric. They could have multiple modes and multiple classes. And if you still use the classic approach to address this problem, we may not be able to close the loop, and the solution again will not be as good as we expected. And this is exactly the motivation of using this approach to look into the problem from a data lens. So ideally, once we get a big data, we get a lot of data, we try to see how can we establish a bridge or establish a link from the data to the decision. And this could be really kind of set up in two ways. One way is we could think about machine learning and data science as a very effective tool and effective approach to extract useful information from this data. And again, this data could be real-time data, could be historical data, or could be forecasting data. And then once we have these very nice machine learning models and algorithms, we want to establish a framework or methodology to organically integrate them together with the existing mathematical program framework. And the whole thing together, if we combine all these things together, we think it's like a crystal ball. This could become data-driven decision-making framework. And one thing I do want to argue here is that this whole framework tends to have a very nice property in the way that it combines the data-driven system on the left-hand side here with the model-based system on the right-hand side here. Because traditional optimization problems are typically very challenging to solve, especially when we have mixed integer decisions here. And also the other perspective I do want to argue here, and hopefully to illustrate this concept in the next few minutes, is that this integration could lead to new and better modeling framework, but also fundamental theory and new algorithms. And very soon, I will show you later on that we will have a lot of applications of this framework in terms of manufacturing, in terms of sustainability, energy systems, and agriculture. So one point I want to point out is this is definitely not a new method, and always we are standing on the shoulder of giants. In certain way, you get to see the paper, the very nice review paper and survey paper by our opening plenary speaker yesterday, looking into artificial intelligence and chemical engineering. And one particular point I want to quote here is that the future is essentially try to integrate the first principle model with the data-driven model and pursue a hybrid modeling paradigm. And this is exactly the same way as we are thinking in this direction here. So moving forward, in the mathematical programming community, this concept has been around for a few years, but it's definitely relatively new. So the pioneer work was done in Stanford in the area called distributed robust optimization. But this was highly restricted to a certain case that involved the second-order statistics. Then a recent piece of work focused on chance-constrained stochastic program. And a lot of focus in the past few years is dealing with something called robust optimization or stochastic robust optimization. And a particular reason to deal with robust optimization is the balance between the solution quality and the computational tractability. So in this area, the pioneer work was done by Dimitri Basimas at MIT and was just published a couple of years ago. The idea is looking into this called data-driven static robust optimization, essentially try to establish an organic connection, organic link between a machine learning model and an adaptive robust optimization model. So my group has been making some contribution in this area as well, and in particular, I want to focus on this specific piece of work in the next 20 minutes, just to illustrate you some basic ideas of the theory and the methodology. And then in the later part of this presentation, we'll get into more applications in terms of operations, in terms of control, in terms of energy systems, and manufacturing. So before we get into the specific details, let me try to use a few minutes to make sure everyone is on the same stage. So let's review some very brief background of optimization theory, and this is something we call robust optimization. So you can see a very interesting photo here. This is the rear bridge, and essentially a club, just a few months after its construction. And this was done in US, which was built about 100 years ago. So what you can see is almost all the suspension bridge is running in a similar way that we want to design a system that could resist or they could tolerate certain level of uncertainty. And if you really try to design and develop a system that doesn't really consider uncertainty, eventually the solution could be meaningless, even though it could be optimal. So one point we want to argue here is that robustness is really the first order effect, and it could make a huge difference in the final decision-making process, no matter it's manufacturing or control operations. So from a mathematical perspective or from a theory perspective, this is a very simple illustration optimization approach. So we know the typical optimization method is if you have some kind of functionalities, hopefully a non-convex function, something we really like as a chemical engineer. So the solution process is really having a ball just rolling down a hill, right? So the way it works is once you have a new starting point, you use some kind of Newton's method or nonlinear gradient approach to find a solution, they give you the minimum objective. So now let's take a step forward and assume the parameters in the model involve some kind of uncertainty. Like, for example, in this case here, the P is no longer a single point, but involves some kind of derivations, with a delta P, which is something like a confidence interval. Then in this case, you are not going to put a ball under the valley. Instead, we're really trying to put a disk. Okay, like in this case, it's a disk trying to go down the valley. So if you look at the difference between this solution and the other solution, the key difference is the sensitivity to the uncertainty. The first solution here, without considering uncertainty, could be highly sensitive to any parametric uncertainty, any changes or any difference in terms of kinetic coefficients or any changes in terms of demand and supply. While the other solution here, although the quality is not as good as the previous one, it tends to be more robust, robust against all kind of uncertainties. And that's the key idea in the end in robust optimization. Try to find out something that is best, worst case. Okay, so best, worst case here is somehow defined as a min-max function. So this was the whole motivation of robust optimization and robust control, starting from 1970s. And the pioneer work by Soister, essentially looking to something called static robust optimization, try to maximizing a function with the minimum case here. And this idea essentially involved two major ingredients. The first one is something we call decisions. And decision variables here are defined as X. In a classic setting, all these decision variables are really met here and now. So there's no flexibility to adjust decision over the time. The other important component is about uncertainty. And this was defined through something called uncertainty set U. So this uncertainty set is usually defined based on some kind of prior information and somehow constructed in a very simple assumption in the early days. So as a consequence, the theory was constructed or developed back in the 1970s, but it hasn't been widely used because the solution from this approach tends to be highly conservative. But everything started to change over the past 10, 20 years, and one of the major changes is to improve the decision process. So in about 2000, about year 2000, Bentall and Soister and a few others started looking at something called adaptive or adjusted robust optimization. So with this approach, we tend to partition the decision into two parts. Some decisions are made here and now, and some are made wait and see. Okay? So here and now decisions are not decisions you have to make by all means before you observe all these uncertainties. It's like when you design a process, design a chemical process, you need to determine all the decisions right now before you see what would happen to the demand or what would happen to the process fluctuations. And all the wait and see decisions are somehow we could adjust it after we observe this uncertainty information. So by introducing this sequential decision-making approach, we tend to give more flexibility to the system, and this is something that we could lead to a less conservative solution, or somehow you could say better solution quality in the end. And this recourse decision could also address some feasibility issues. So as I mentioned earlier, the other important gradient in robust optimization is about uncertainty set. And the key idea here is try to see how can we model uncertainty from a systematical way and from an automatic way. So the classic approach, again, back in the 1970s, is very simple, a very brute force approach. Any uncertain parameter, once you get it like U here, we just get an upper bound and lower bound, and that's it. Like today's temperature is between 10 to 20 degrees. So I said the uncertainty set is between 10 to 20. So this is a very simple way to handle the problem. It's treatable, but the solution quality, as you can imagine, is not so good. So back to later 1990s, there are some advances looking into improving the solution quality, but the price here is we have to introduce some kind of nonlinear function to capture the uncertainty correlations and other informations. So in early 2000, there was really a step change in certain way that Basimas and Sim at MIT started proposing an interesting idea using budget uncertainty set. So the key idea of budget uncertainty set is essentially using L1 norm to capturing the correlations between different uncertain parameters. In the end, you end up with something like this, a diamond-shaped uncertainty set. And this approach tends to be very nice in a way they could improve the solution quality significantly. But again, the major drawback is that this approach could be only useful for the independent uncertainty sets and also for symmetric cases. So ultimately, or in theory, the very best uncertainty set should be flexible enough to capture any shape and any structure. Think about a polyhedron, something like this with many faces. They could take any shape we want, and it could be in any kind of structure. And somehow, ideally, we want to model them through a system of linear equations or inequalities to capture all the possible uncertainty realizations without sacrificing the solution quality. So here comes the fundamental research questions, okay? So what has been done so far are really something called classical methods we talk about. So these classical methods are really based on some kind of fixed geometric shape. It's either a box, a diamond, or what kind of shape we want to define up front. And second, all these existing methods are really convex. And certainly there is a good reason to make them convex, because convex optimization problems are always easy to solve. And the third one is something we call one set fits all, because they always try to use one set to fit the entire space of uncertain parameters. And there's nothing we can blame on existing methods, because all these methods are really developed without considering the data. And all these methods are really developed without using any artificial intelligence or machine learning techniques. So now if we could think about this way in a different perspective, how can we jump out of the box? So maybe you could ask some fundamental questions like this. Let's say if you have a bunch of data like this, with just two simple uncertain parameters, U1 and U2, with certain distributions, how can we derive the best polyhedron uncertainty set to cover the entire space? And certainly machine learning could help us to do that. We could use all kinds of machine learning probability estimation methods to come up with a nice boundary of this uncertainty set and cover them. So somehow we could argue this could be optimal polyhedron uncertainty set, which is a classic problem that people really want to solve over the past decades. And now with machine learning and deep learning, this could be possible. But how about we take a step forward? Still for the same set of data, can we use something that is not convex to cover this region? And the answer is maybe yes. If you look at these two particular shapes here, it looks like a non-convex shape. This is non-convex shape. Non-convex one tends to have a better structure compared to convex one, in somehow that we could really eliminate this area, which never has any occurrence of the uncertain parameter. So one idea here is to use the piecewise linear uncertainty set to cover this region, even though in the end we end up with a non-convex region. All these piecewise linear models could be captured very nicely through the mixed integer programming framework. But one step forward is, do we really have to use one set to fit all of them? How about use many simple sets? And this is another further improvement from existing ones that you can see here. From the entire space, you could partition into small, basic uncertainty sets. And these basic uncertainty sets would cover the entire region in a way that is better than this one-size-fits-all approach. So this is just some kind of basic ideas and motivations. And I want to argue in the next few pages that machine learning and robust optimization could really lead to a new data-driven methods, but also the novel and previous incredible optimization paradigm. So in the next 20 minutes, I'll really focus on the theory and methods. And then in the last 20 minutes, I'll focus on a lot of applications in all the domains. Okay? So let's begin with a very simple motivating example, just to make sure everyone is on the same page. So now let's just, again, consider a very simple case with only two uncertain parameters, U1 and U2. And you can see these two parameters are somehow correlated in a certain way, because most data are in this region, and we do have some outliers on the upper right and lower left corner. So if you use the classic box kind of uncertainty set, as we mentioned earlier, it's really looking at upper and lower bounds. So once you're looking at upper and lower bounds, the uncertainty set you get in the end is really a big box to contain everything together. And this approach tends to be pretty bad, whether we have to hedge against uncertainty in this blank area, which has nothing to do with our occurrence. So with a little bit better approach, coming into the early 2000, is something called budget uncertainty set. And these budget uncertainties tend to have a better structure compared to the previous one, and somehow they could be resistant to some outliers. But with the data-driven uncertainty set that we will introduce in the next few minutes, what you can see is we end up with a very nice and very compact representation of all existing uncertainty parameters. In addition, we are also hedging against all these outliers. So this is really the power of introducing machine learning into one of the traditional areas and to try to address a classic hard problems that we have never able to solve. So what's behind this theory? This is really some kind of classic approach in certain way. With a lot of data we get, we use variational inference to construct something called directional process mixture model. And then this directional process mixture model was proposed about 10 years ago by Michael Jordan and co-workers in Berkeley. So this is essentially a Bayesian non-parametric model, a classic class of optimized machine learning techniques. And the key idea here is using the state breaking measure to construct the number of components automatically based on the structure and complexity of the data we have. And this is some kind of graphic model so you can see for uncertain data. So once you could be able to construct all these components, we'll be able to look into the predicted posterior and eventually build up all these uncertainty set based on the data we are going to address. So based on this framework, we could construct this uncertainty set using this called L1 norm and L infinite norm. So L1 norm is essentially this diamond shape we are talking about earlier. And L infinite norm is pretty much the upper and lower bounds we are mentioning earlier. So in this case, we are looking into the intersection of L1 norm and L infinite norm. So the outcome is that if the L1 norm bomb is within L infinite bomb, then we end up with the same as this diamond shape. If they overlap a little bit, then we end up with kind of like a polyhedron shape, okay? But again, this is just pretty much one of the basic uncertainty set. And the key idea is using multiple basic uncertainty sets to get a high fidelity description of all uncertainty information. And then based on this uncertainty set, we could quickly put in the optimization framework or adaptive robust optimization framework in this kind of multi-level mini-max mini problems. And the major feature of this model is that the size of the problem will largely depend on the data we have, depending on the data structure and depending on the data complexity. Additionally, this is a multi-level optimization problem, which would have a very nice feature in certain way. Or in particular, it's different from a classic adaptive robust optimization in a way we do have an actual maximum, which is corresponding to each component or corresponding to each basic uncertainty set we have in the model. So the advantage of this approach is that it could be adaptive to uncertainty, it could be less conservative, and also it could capture the nature of all uncertainty data. But in the end, there's no really free lunch, right? So the price we need to pay here is we have to deal with this multi-level optimization problem, which is hard to solve. So to address this computational challenge, what we did further is to explore a model structure. Eventually, we could turn this multi-level optimization problem into a single-level semi-infinite problem by exploring these extreme points in the lower-level polyhedron divided by the constraint of the lower-level problems. So based on this property, we could develop a kind of a very efficient decomposition-based algorithm based on column constraint generation and solving it by a sequence of sub-problems. So I will not get into details here, but the key idea, what you can see, is that we're really iterating solving a master problem and a sub-problem. And then by adding these cuts, optimality cuts and feasibility cuts to the uppercase problem until eventually end up with the optimal solution. So this is the end of the theory. And let me show you a few examples. Hopefully they will be easier to understand and illustrate the concepts here. So let's think about a very basic problem, which is the same kind of data we mentioned earlier, two uncertain parameters, but in the context of a very small numerical example. Here you get x1, x2 are the first stage stations, and you get y1 and y2 are the second stage stations. So the u here, the u set here is the uncertain parameters, and are defined by this uncertainty set u. So we try to solve this problem using three different approaches. The first approach is the classic box standard uncertainty set. The second approach is the early 2000 approach based on the budget uncertainty set. And the third one is the one proposed earlier using the data-driven measures. So what you can see is a clear difference in terms of structure of uncertainty set. The box one tends to have a very large region. So in the end, the objective function of something is we're trying to minimize the cost it tends not to give you a very high cost in this case. The budget one tends to have slightly improvement, reducing the cost from about 415 to 431, but still it's not as good as we would expect it. The data-driven one tends out to give you a very compact representation of the uncertainty information, and in the end, the minimum cost could be significantly reduced. So the difference between objective function values here really illustrate the value of data and the value of using data in our decision process. Because otherwise, almost all existing optimization methods and theory are not based on the data. All of them are really based on the mathematical theory and classic computational methods. But by incorporating this data into the decision-making process, one example here is you can see we significantly reduce the cost by almost a quarter to a third. The other example, which is pretty much the same problem, but now we change the data distribution. And what you can see here in this case is that you want you to specifically correlated in certain way, they are negatively correlated. And somehow also you can see the data has only one component because it's a single cluster. It's very easy to illustrate. So very similarly, we can solve the problem with three different approaches. The box one, the budget approach, and the proposed data-driven approach. So what you can see is, again, very similar case. The box one gives you a relatively high cost. The budget one slightly reduce the cost. The data-driven one gives you the minimum one, okay? And if you're looking at the data coverage here, the box one tends to cover everything we have. The budget one has a certain kind of overlap with a certain data, and the data-driven one tends to adjust the percentage so that everything covered in this blue box will be the same as the one covered by the yellow box. So that the data coverage, so that they will be equal in certain way. But another interesting exercise we could take is try to see how we can adjust the data coverage and see what would be their impacts to the solution values. So this could range from covering from 0% data, which will eventually be a single point here, a point estimation, to covering 100% of data. And what you can see is that the blue line is essentially objective value or the cost, if you wish, from a data-driven approach. And the yellow one is the optimal solution from the budget uncertainty set, which is in the middle. So in almost all these cases, what you can see is the data-driven one tends to give you a lower cost, and that really illustrates the concept of applying data-driven approach and incorporate it into existing optimization methods to reduce the cost and improve the solution quality. And more importantly, if you're looking at two extreme cases, essentially trying to cover 100% of all the data we have, then this budget one, this budget approach, will be expanded to be eventually something like a big box, okay? But then this data-driven approach tends to be very flexible, and they could adjust its structure to very nicely capture all the data we have in this system. Another example is really just going to from 2 dimensions to 3 dimensions, just to see how it looks like. And again, in this case, here we have 3 first-stage decisions and 3 second-stage decisions, and all the uncertain parameters will be staying in this 3-dimension space. So what we get in the end will be kind of like a big chunk box for the box type uncertainty set. Now this really become a big box. For the data-driven one, we end up with a very nice polyhedron over each particular clusters and each set of the data we have. And this is for the case of 100% data coverage. Moving forward, if you're trying to make the budget equals to 2, then this particular budget uncertainty set will be something like this, okay, covering most of the data, about 18%. But for the data-driven one, the size doesn't change that much. Instead, the data coverage will be slightly different. When budget equals to 1, essentially go to a more aggressive case, the data coverage is about 40.75% in this budget uncertainty set case. Then the data-driven one, you can see, will be covering the same amount of data, but always giving you a lower cost in the end, okay? So these are just basic illustrations of some of the concepts and ideas from this theory and methodology. So let me give you a very quick summary about what we have done so far. This idea here is based on a union of multiple basic uncertainty sets. And these uncertainty sets are convex, they're easy to compute, and very efficient in terms of solution. So we try to use this basic uncertainty set to cover the entire uncertainty space. And in this idea here is that even you have some overlaps between these basic uncertainty sets, it's okay. Why? Because each uncertainty set eventually lead to a set of constraints in an optimization model. And you do have some overlaps between constraints, which will not affect the solutions process at all. The second idea, which is kind of important, is that this method is really beyond clustering. Okay, we are not really doing clustering. It's clustering plus density estimation. So one example you can see earlier is that even in the case we have only one cluster, the solution approach tends to be very efficient in a way to capture what it looks like in terms of data structure or orientation. The other issue here is even for this one cluster case, we always perform better compared to the classic optimization methods. And if you are familiar with optimization theory, especially familiar with mixed integer optimization, some of you may ask, why don't we use convex HAR? Okay, convex HAR is essentially a tightest representation of some discrete points in the space. So ideally, yes, we want to use convex HAR. But to derive a convex HAR for an arbitrary number of points in a high-dimension space is almost impossible. Why? Because if we could derive convex HAR for any arbitrary number of points, you could easily show that any integer problem problems could be solved as an linear problem problems. Then you complete this proof of P equals to NP. And that's really a counterexample in a certain way. So convex HAR is not always not possible, but we could get as close as we can to the convex HAR through these machine learning techniques. And the third point here is that this approach is really scalable. It could be applied to large scale applications and could be illustrated through higher dimension cases. So one particular application is a success story we did with one of the major chemical companies in the US, Dow Chemical at the time, and now they call Dow DuPont. And this addresses the problem of production scheduling. So what you can see is they have a batch process with 4 raw materials, 6 intermediate products, and 4 final products. So the scheduling objective is to maximize the profit and subject to a number of constraints here. So the major uncertain parameter in this case comes from the demand, comes from processing time of the batch process. And what you can see is all these data are really asymmetric, multiple mode, and correlated. So by solving this problem, if you use the classic approach, the box standard uncertainty set approach, we end up with a Gantt chart like this. Okay? And you could argue this Gantt chart doesn't look very nice because some of the outliers in the data certainly affect the processing time. So it turns out to have some kind of longer processing time in certain stages. But more importantly is if you look at the profit, the box one and the budget one both gives you a profit about $34,000. But if you use the data-driven approach, we end up with a profit of $46,000. All right? So that's a big difference in terms of $12,000. And what you can see is gaining $12,000 of profit, or 1/3 of the profit, is really because of the utilization of big data in this classical production scheduling problem, which has never been done before by any other existing research or practice. The other application is looking into process planning, and this is a very classic process planning problem with a very large chemical complex, 38 process and 28 chemicals, looking into different suppliers, different markets, and involve multiple processes. So here we do have a relatively higher dimension of uncertainty space. All the supply and demand are subject to uncertainty, and there are tens of thousands of uncertainty data we can collect it from historical database. The objective here is to maximize net present value and subject to a set of constraints involve capacity expansion, investment, and so on and so on. So by solving this approach, again, comparing with the classic box standard approach, the budget one and the proposed data-driven one, what you can see is there is a clear increase or clear improvement in terms of net present value. They improved from about 761 to 857. So there's, again, at least 10% increase in terms of economic performance. And somehow you could also argue that even you change these parameters in the uncertainty set, the most conservative approach, let's say 806, will be still higher than all the solutions you could get from classical approaches. So again, that illustrates the idea and the value of incorporating data into this decision-making process. So these are some details about capacity expansion decisions. On the left-hand side is really the solution coming out from a box kind of uncertainty set. What you can see is each number here. The uppercase shows the process number, and the bottom here is the capacity in terms of kiloton per year. And on the right-hand side is the solution from a data-driven approach. So they tend to be quite similar in a certain way, but some decisions could be completely different. Like in the classic one, you don't have this particular process. In a data-driven one, you do want to build this particular process. The last page here, essentially of this example, just gives you iterations of these algorithms. Because we mentioned we have to solve these problems through an iterative process between master problem and sub-problems. So eventually what you can see is the convergence will be achieved when the upper bound decrease and the lower bound increase until the gap is closed from about 94% to 9% and eventually get to 0%, which is really the optimality gap or gives us the optimal solution. So this is pretty much a brief summary of the first study we mentioned earlier. The idea is try to incorporate this directional process mixture model into the classic adaptive robust optimization problem. It turns out that this merge between machine learning and robust optimization lead to a fundamental game changer in terms of theory and in terms of methodology. So if you're interested, that's the paper that you could take a look. So one thing we did, which is really a step forward, just to think about what we really deal with, what are the kind of data we are facing in the chemical process industry. Attributes or some kind of label informations. For instance, if you have a data from energy panels, solar panels generation, we could also have some labels in terms of weather condition. That today tends to be cloudy, yesterday tends to be sunny. So with these features, we could have some extra information that you could utilize or leverage through this decision-making process. Similarly, for a chemical process, we tend to have different operating modes. And this information has to be captured in a certain way together with all the numerical values. So one step forward we did is that instead of considering a single derailleur process, we're looking into a group of different derailleur processes. And the whole framework here is pretty much a combination of classic maximum likelihood estimation, trying to figure out the groups and understand the clusters, versus a group of specific derailleur process mixture models. And this turns out to be something called stochastic robust optimization framework that could scale up very quickly to millions or billions of data points with different attributes and features. And this was a paper that just came out last year. So this approach can also be applied combining with other machine learning techniques. So one interesting application looking into something called support vector methods. And this is one of the methods called support vector clustering with generalized intersection kernel. So with this approach, in the end, we end up with a quadratic programming problem, which is kind of computational challenging to solve. But a nice property of this approach is it could very nicely capture the geometric structure and also control the fraction of outliers of the system. And they could be similarly applied to all kinds of process operation problems in terms of planning and scheduling. And the other interesting extension is looking into very classic methods called principal component analysis that many of you probably have heard about. But with PCA, we could capture these orientations of data. And then with these orientation of data, we could use some kind of kernel smoothing methods to understand where the data lie from and what are the projections for reconstruction. So one of the direct application is on control system design. So on the right-hand side here, what you can see is one of the classic small-scale control system design. Because methods like PCA and kernel smoothing tends to be very efficient in terms of computation. So they could be used in real-time computation and looking into a lot of data-driven robust MPCs. And some of the recent work we are doing here is using deep learning. And this is not surprising, because once you run out of all these classic machine learning techniques, we could always time to go to deep learning. And one of the deep learning techniques that we are dealing with is a generative modeling, or we call GAN, generative adversary network. This is the idea of having a generator and discriminator to try to capture all the uncertainty informations. And this will be particularly useful when we do not have a sufficient amount of data to capture the uncertainty informations. And this framework could be useful in terms of way we could incorporate them into stochastic chunks constraint programming and achieve much better solution compared to the classic stochastic programming methods. So all we have talked about so far are pretty much fundamental theory methodology, but certainly these methods could be applied to a variety of domains. One of the applications with some of the collaborators in Asia is to apply these methods into one of the existing and real polyethylene manufacturing plant. And this specifically focuses on their steam systems. Essentially, we have a lot of data coming out from their turbines and all the major process historical informations. This data-driven data robust optimization framework could be readily applied into the scheduling and the design of all the turbine systems and steam systems to reduce the energy consumption and also to reduce the cost. We could also similarly apply this framework to some kind of electric power systems. Once you look into these wind and solar generations, they are subject to all kinds of uncertainty. And this will be one of the interesting opportunities to leverage the big data into our decision-making process. Another application, which is pretty much more chemical engineering, is looking into more traditional gas absorptions or gas separations. And this is the collaboration with some of my former colleagues at Northwestern in the way that they are developing materials, something called metal-organic frameworks. And these materials could be synthesized in the lab with a lot of uncertainty, or they could be modeled through molecular simulation, which could be highly computation intensive. And from our perspective, we try to run a large-scale process simulation optimization building upon the partial differential equations. So this is an area that we could leverage some of the deep neural network systems and also some of the data augmentation approaches to capture this uncertainty in the material synthesis and also help us to optimize the pressure swing absorption process. And there's a nice looping here, where we have material properties input from experiment and molecular simulation, and also we design targets fitting bed into material design and decision making. The other extension, which is more in the control and automation area, is one of a recent study we did looking into a stochastic model predictive control. And this is the idea to try to see how this stochastic model predictive control theory could be merged with the data-driven robust optimization. It turns out that we are more interested in fundamental theory, but the application did get a lot of attention. So we did apply this framework to one of the real building at Cornell. This is called Topeka Lodge. In the end, we were able to run this something called active online learning of the system because MP is running in an online manner. And what we did in the end is we did save about 10% of energy through 1 year of demonstration. So very quickly, some of the news media just pick up this story. Of course, they changed the titles. They said to conserve energy, AI helps clear the cloudy forecast. And of course, you could also see some other new titles in the news report showing that the data-driven approach could save energy, whatever weather is. It turns out this article was published in early this year when they had this Davos conference in World Economic Forum. So our friends in Switzerland, they tend to pick up one of the photos from their particular region covered by snow and showing us how these machine methods could slash energy bills in old homes in a certain way. And it was also captured by a few other media in Middle East and Asia in general. So the other extension, which is going to be kind of like a little bit non-traditional area of chemical engineering, is on food and agriculture. And this is a collaboration with my colleague, Professor Eb Struck. So the idea is looking at irrigation systems. If you're looking at irrigation systems, the major uncertainty really comes from weather forecasting. The precipitation forecasting is something subject to a lot of in-depth online data analytics needs. So in this case here, we use this data-driven robust optimization method coupled with model predictive control to see how we could reduce the water consumption and how can we achieve a better performance compared to the classic approach for growing these crops and fruits. So it turns out that we were able to achieve more than 40% saving of water through a demonstration in the real Cornell orchard there. And this also demonstrates the value of data as a very important asset for optimal control problems. So the holistic framework of this approach, of course, documented in this IEEE TCST paper, is under this area or under this idea called gray box digital twin. So the key point is the app and his friend and his group are really developing these microfluidic sensors. And my group is really more on the process system side, developing control systems and optimization engines. Eventually, everything could be combined together. And going back to the very interesting idea that Professor Fengqi mentioned yesterday, to combine the data-driven and the model-based systems together. And in this case, looking into the smart and data-driven irrigation systems. So the last application I want to show you very quickly is one of the ongoing projects we're doing, looking into battery systems engineering. So one of the very interesting perspectives here is we want to try to bridge the fundamental electrochemistry systems within the battery versus all the driving patterns, the mileages we have in the drivers, and all the big data we collected from all the battery usages. And this turns out to be a very interesting way to close the loop in the control system and also to balance the performance, balance the aging, and the safety of the entire system. And again, we can see data really play a very important role in this decision-making process, not only as the input parameters, but also help us to better design and develop our decisions through these frameworks. So let me conclude here, and I hope through this presentation I convince you that we do have a very nice integrated and I would say optimal decision-making framework that kind of merge together this data-driven approach and a model-based approach. It also leverages this data analytics for optimization under uncertainty, which is something that has not been done before in an extensive way. And somehow I also argue that this merge or this combination really bring the theory and methods in both fields to the next level. It helps machine learning to transform from data to information and also to the last level to the optimal decisions. And it addresses some of the very fundamental problems in mathematical programming, which will never be all based on the existing classic methods. So this will be something, really empower machine learning to the next stage and also support the scientific discovery of the new and more powerful optimization paradigm. And there are a variety of applications that could range from manufacturing to sustainability to energy systems to agriculture and many, many other areas. That I could see this could be a very interesting direction to pursue in the next few years. So with this, I want to thank you very much for attention. And again, I want to show you some nice photos of our campus. You're all very welcome to visit us at your convenience when your schedule allows. Last thing I should say is obrigado.
Well, we have time for some questions.
Good morning. My name is Filippo. We have been done some works with Gaussian mixture models, but we have some problems interpreting the higher parameters and the results. Do you have any tricks of the trade you want to share with us?
Yes. So Gaussian mixture model is one of the co-parametric approach. In fact, there's one slide. I don't think I showed it earlier. I could probably just pull it out quickly. The reason we did not use Gaussian mixture model is exactly because of this tuning process that you are mentioning. Where is it? Sorry. Yeah. So if you are given a set of data and you want to use Gaussian mixture process, the key point here is we have to define these parameters up front. You know, things like the weight, the means, and the the covariance matrix, or the standard deviations. And these numbers are something that we have to specify up front. And this could be always a challenge in a certain way because we don't understand the structure of the data before we really solve it. And that's why this is one of the major drawbacks of parametric approach, where the space is somehow finite. So in this example here, what you can see is the set of data has three modes in a certain way. If you just use 6 parameters or 2 components of Gaussian mixture model to fit it, the fitting may not be as good as we expected. But instead, if you think about a different approach, for instance, the dirichlet process mixture model that we mentioned earlier, it turns out that this is the model that has infinite parameter space or infinite dimensions. And with these infinite dimensions, they could automatically infer a number of components we need and a number of picks we want to use and help us to understand what's the underlying data structure and eventually capturing the entire distribution in a very systematic and optimal way. So that's the key reason we did not use Gaussian mixture model. But certainly Gaussian mixture model could be helpful in many cases because it's easy to solve. You don't need to deal with a very challenging variational inference approach, among others, and it's still widely used. But exactly as you mentioned earlier, defining these hyperparameters is very challenging, and training them could be another challenge as well, because a lot of numerical issues that you will encounter in the expectation maximization methods.
Thank you.
Thank you for this nice presentation. I wonder about the uncertainty of the uncertain parameters, because the robust optimization, those that the square sets, it's too much robust. And there is a compromise of this uncertainty based on the data-driven approach. But this data-driven, there is some uncertainty also in the data you have, and how the impact of this uncertainty of your uncertain set?
Well, that's a very good question. Uncertainty of the uncertainty sets. So I think the idea is we try to make uncertainty set as optimal as possible to really capture all uncertainty. But in the end, of course, the model, the uncertainty set, will be as good as the data we have, right? If we argue that we don't have enough data or the data is not as good as we expected, maybe some 40 sensors out there, they could concern some issues, then this uncertainty could be a problem. But that being said, this whole framework has 2 particular components that could deal with this approach. So as I mentioned earlier, we do have a lot of nice models from dirichlet process mixture model to PCA and so on that could deal with all the outliers. And this is one way to deal with this low quality data. The second approach, which is something we are talking very briefly just now, is using these data augmentation methods. Because in the case that if we don't have enough data right now, but we still want to capture uncertainty in a reasonably optimal way, then you can infer this uncertain information using something like generative adversarial network and many other methods from deep learning to construct and develop artificial synthetic data and eventually build up more reasonable and reasonably optimal solutions to address these challenges. But eventually, of course, nothing is perfect. Somehow people argue all the models are wrong, but some are useful. So this is one of the examples here. It applies to statistics and also applies to machine learning and all the problems we are dealing with.
Any more questions? We have time for some questions.
Well, actually, the people don't ask it, but I have another question for you about this idea to bring together that data-driven approach with the knowledge-based approach, this hybrid system. I would like to hear a little bit more about this, how your impression about it, because nowadays there is too much moving only to the data-driven approach, forgetting all these knowledge-based things. So I'd like to read more comments about this approach.
Yes. Thank you. I think that's a great question, and I think, well, Professor Fengqi is the best person to answer it. My personal experience is like this. So if you're looking at the history of engineering and physical science over the past centuries, we've been really focusing on mechanism-based models. We try to understand the kinetics, we try to understand all the transport, fluid dynamics, and all the details. And we build all these models really based on first principles as much as we can. And of course, all of a sudden, people argue that once you get enough data, once you have very nice algorithms coupled with very powerful computation architecture like graphic processing units, you could get everything done by neural network. And that's really going to be a long-term solution. At least from a near term, neural network could solve some problems, but not as good as what we have. So one idea, which is something that Professor Fengqi also emphasized yesterday, and also relevant to our experiences, that is, if for a model or for a system, you have a very nice model to capture what's going on, you have very nice first principle knowledge and information, then why do you need to use data-driven approach, right? On the other hand, for something that you don't have very clear first principle model, or maybe the model is not so accurate in a certain way, then the data-driven approach will go out very well. So this is the same in the control community in a certain way. You could build these model-based control systems based on process model, or you could build them based on system identification of input-output data. And that's the main idea we have in this called data-driven robust optimization. Because we believe optimization problems will be still the best solved through mathematical programming. Because those are theories, there's algorithms out there that could help us to make decisions very effectively and very efficiently. On the other hand, for the particular piece of uncertainty information, that is always hard to capture directly through a simple theory or simple model. And it turns out that this is the area and opportunity for machine learning and deep learning to play an important role. And for the specific example we mentioned just now on irrigation systems, that's a very interesting problem. In fact, it's a very simple problem. You just want to control the balance of the water in the soil in the crop. But in the end, it turns out to be very challenging because the water transport in the crop is really a microfluid process. Nevertheless, we could write out all the partial differential equations like what we did in chemical process. However, for the weather forecasting, it's always full of uncertainty. Because when I arrive on Saturday, the weather forecast says it's going to rain on Sunday, but in the end it did not, right? There's no way you can come up with a perfect forecasting, but this uncertainty of forecasting is something you can really capture through some sort of data-driven approach. And that's the opportunity in the end we could demonstrate through some of the energy control problems, energy control of specific buildings. By running the entire data-driven approach for 1 year, we could save energy for up to 10%. And for irrigation systems, if you incorporate this weather forecasting information into the control system, we could reduce water consumption by more than 40%. So there is really a value of using the data, but the key issue is how can you use the data in the right way? Can we fully use the data to replace all the first principle knowledge? I don't think that would happen in the near term, maybe in the long term, but at least in the near term, the best way is to probably combine these two things together and leverage the strengths of both sides.
Well, let's say thank you to Professor Yu